identify some problems at first, right? And more detail. Uh, First one is business unit domain, and second one is engineering domain, and last one is operation domain. The feed process, I think the front end loading is very important in feed process because the conceptual design and some development of the process is just this process. And then I told you the risk and opportunity management like this. T TECOP is technical, economic, and commercial, organizational, and political. So that is related these issues. So we have to identify some issues before we starting the project. In Ocean Plan project, the I think the technical design is more important than an economic or commercial. I think because as you saw, the video in the video, the complicated design is in Ocean Plan. So I will show the to manage some this effect in for the video.
Managing risks in marine projects is crucial for success. One key risk is environmental impact. For instance, during a dredging operation, we must assess sediment displacement and its effects on local ecosystems. Implementing a robust environmental management plan can mitigate these risks effectively. Another significant risk is equipment failure. In a recent offshore wind farm project, we faced unexpected downtime due to a crane malfunction. By conducting thorough pre-project inspections and regular maintenance, we can minimize such disruptions. Weather conditions also pose a challenge. During a marine construction project, we had to halt operations due to severe storms. Developing a flexible project schedule that accounts for weather variability can help us navigate these uncertainties. Lastly, stakeholder engagement is vital. In one project, miscommunication with local fishing communities led to conflicts. By fostering transparent communication and involving stakeholders early, we can build trust and reduce resistance. Incorporating these strategies not only enhances project resilience, but also promotes sustainable practices in marine project management.
Usually we can manage some risk at Ocean Plan engineering and or marine project. So for attention, yeah, and question, feel free to ask.
Right? Not simple subject. This is the second part of it. So here. So you can see I already explained about EPC. What is EPC? Say again, what is the EPC? Short name? EPC?
Engineering procurement.
Engineering, procurement, construction. So engineering means in general it's a design, more than design. So EPC, the field is front before EPC. So we already see that EPC contract. Last week we heard about EPC contract. Who will be the contract body? So in the old days, or 10 years or 20 years ago, engineering companies such as Technip was the main contract. But as the project gets bigger, $1 billion, then they give up to make to be a main contract. And then instead the big shipbuilders like Samsung or Hanwha or Hyundai, they are now more becoming a EPC contract. But before the EPC contract, we usually do it. So between them, there is a major work of contracts between owner and the constructor, EPC contract. Before contract is a fee. So it may say it can be a kind of basic design or ship or concept design or basic design or initial design. I'm trying to explain about more detail on concurrent engineering and transition management, and SPM is a short name for supply chain management. Supply chain management is related with procurement. You need to say one engineering plant is made of 1 million pieces of elements. We need to collect. But most of them are procured, purchased from outside, provided by outside. So that supply chain is a procurement. Because if you want to buy, say, boiler or engine, the boiler is made of by another company, big company, but that company also have a suppliers. So it is something like a food chain. The supply chain is, so we call this is a hierarchy of supply chain. The hierarchy of supply chain. So we call this is a OEM or assembly, or say for the car you may say Hyundai Motors. Today is not good. Toyota say Toyota. Because Hyundai is also shipbuilding. Toyota. Then there is suppliers. Oh, probably we call this a first tier. Supply. Oh, then second tier, third tier, fourth tier. There's a so it's a supply chain. Connections. And then process design. Process design is usually concerning about chemical process for the ocean plant. Process can be a very general word, but usually in ocean plant they are saying chemical process. So many of us expert coming from chemical engineering. They do this kind of. And PNID is another drawing, name of drawing. You see more this. And motivation, because the ocean plant is a complex, interdependent part of million parts. Million of them is interdependent. And also independent means that the whole system is independent. You can say the closed system. Very similar to, say, to airplane. Airplane is also closed system. More closed system is a space shuttle, space craft. That is more closed. I mean, the external boundary interaction is less, more or less. Comparing to this building is, you cannot say it's a closed. And security or safety, and also that's why we need to have a good management. Yes. Oh, video is working. Yeah. So there was a big disaster 14 years ago around the Gulf of Mexico. Place was there. Okay. So there has been a big explosion and fire, and people was lost. And also there has been a film. Have you seen this film? Only one? Okay. Yes. It is a British Petroleum company. The owner of this project, BP, British Petroleum. They paid about 10 billion. Oh. 10 billion? 10 billion? That money was lost. Oh, that's it. So then after that, we need to upgrade the safety regulation level. So design process, once again, we start from oil major, something like a Shell. And they detection, because this is for design, not for construction. Yeah. Engineering is the main concern on this chart. So oil major, something like a Shell, they have an interaction with the design office. Sometimes it can be a technique only for designing engineering. And vendors, you can say equipment suppliers. The supply chain here, million pieces should be purchased through vendors. And design basis is usually coming from chemical process engineering or regulation something. Code is a regulation. And specification is contract specification. The contract, usually contract signed with a book of specification. So that can be the design basic functional requirements, specification, regulation, and then there is a for construction. So after mining and inspection, negotiation, and then we provide output can be the construction drawings and specification, and then also purchasing. So PC, EPC, right? So usually there will be a contract signed between EPC contractor and the owner operator. Questions? The similar picture but different viewpoint. Client are there, engineering is here, and the design basis is coming from process design, chemical process design. We call this as a PDP or process design package, coming from chemical operations. And then deliverables is for vendor is put here. Vendor is also there for the design need contact with the vendors to know what is the size of the engine, what can be the weight of the boiler. So you need some information from vendors for the designing. But actual purchasing is coming from through the construction and procurement. So this is the EPC contractors. Quotation and inquiries, and then also there should be another contract between purchasing. Costed inquiry, bill of material, specification. Client is coming again. Every basis, design basis for EPC. Tendering is a contract, call for contract, call for proposal, and work material acquisition for LLI, long lead item. Long lead item, for the car, the mold for making the outer skin of the car. Say bonnet or door and roof is one piece, right? Roof is one piece for one car, right? So big steel plate is coming, and then there is a mold stamping. They make one roof sheet, formed and shaped and cut it. So we call this as a mold or big steel, I don't know, steel or metal press. How can I say? In Korean steel, 붕어빵 기계, right? There's a mold, small mold for cooking. Cooking, there is also, we need a small piece of mold used, right? But it's a big one to make one roof of car in one step. Then how can you make this mold? This is very big, and it takes, say, more than 1 year to make this. And precision on the surface is very important, right? And also the plate is only, say, 1.2 millimeter, something. That's plate of the car skin, very thin. So if you have a making of molding and making a shape, then it can be a spring back there. So you need to have a many calculation of this. So making this mold is very high technology and takes a long time. We call this a long lead item. For the ocean system, you can say the engine of the ship. It takes also, delivery can be at least 6 months, right? 6 months, or may take, depending on the situation. If there's a long queue for the engine maker, it may take more than a year to deliver. For the ocean plant, nowadays, the most long lead item is drill tower, and also, can I remember the name? The rotational, we'll see. Anyway, this is important for construction people. Some item among million piece of items, one piece is missing for 6 months later, then whole project should be waiting. So scheduling is most difficult. That's why they need this. And deliverables, right? Component engineering, so EPC, right. Traditionally, it should be a sequential process. We do designing, we do purchasing, we do assembly, right? That is a natural thing. But component engineering, they want to make a shorter period so that the works are overlapping each other. then it means something like this one. The drawing is produced end of design stage, but procurement started before the drawing is coming. Right? It's okay. Sometimes some drawings are delivered in the middle, but the problem is they purchase started, but drawing changes sometimes. Right? In between somewhere because of other disturbances come. So there are change management is very complicated situation in this way. Change management. Here also change management is important, but this situation more important. More important. But now the market is requiring more and more time to deliver. Right? New item, new product. China, Samsung is competing each other in the market. And another company from Japan, they produce new product, new model, more faster. Say 1 month, new smartphone is coming. The other month, new smartphone coming. But Samsung takes only 6 months or 3 months, then it's not good. So that's why you need to have a speed and time to market. That's why we need to have a concurrent engineering. So market is driving this requirement. But problem is coming to engineering office or construction office. Any changes, complicated work. So you need to know how to handle this situation. So same again, sequential, engineering, design, and bill of material is the million pieces of parts, components. This is a bill of material, we call this. And then purchasing and assembly, all this. But now in concurrent engineering, there is something like, right. Bill of material is divided into several pieces so that they start before engineering finished, right? And also construction is started before engineering or purchase is finished. It should be overlapping. So computation is coming. So that design input early, avoid the changes. If there is a change, the rework, right? Say, started construction, but something is happening to change the design. Engine is changed, or boiler is changed, or voltage is upgraded, or something different. Then they change the procurement, the purchasing different items, or again, or change, or again. And construction, they need to rework. So integration is important, data consistency, because changes, there is a change, but they don't know heard about change. And going on, so that consistency, configuration management, change management. So, right. So process is a chemical process simulation from chemical engineers. And then based on this is a PNID diagram, process diagram. And then based on this process diagram or calculation simulation, you can list the equipment you need to purchase. The size of boiler, size of condensator, gasification is fixed. And then you can contact with the vendors to purchase equipment of this one. And the vendor itself also have a design office. And they produce drawings. And then making this equipment, construction or manufacturing, you can say manufacturing of equipment, and delivery to shipbuilding or EPC contract. But now you need to have an installation of equipment inside the ship or shipping. So that you need to have a foundation. Okay, engineering is the integrity of the plant equipment and is highly dependent on vendor data. Something happening when they are late, they found something is wrong. Number or size or estimation. Estimation means not exact calculation, assumption. But something happens that they need to rework, found out in the late stage, there was some kind of overlapping or conflict, then you need to have a change something like that. So this looks simpler, but it's very hard to do, right? Because at the design stage, there's not enough information available. Right? So quick coordination, display, anticipation. So change management. Need to, did I told you about the Mustang case? No? The picture is not there. How many Mustang? Let me check. Oh. Which one is best? Maybe relative much. This is a Mustang coming car from Ford company, right? Ford company. Copy. Yes. How can I say or say more? Found that the engine was too big to accommodate inside the bonnet in the later stage. That's why they changed the shape of the bonnet in the middle, because the engine size is too big. So coordination between engine department and space design department. That's a problem. It works many cases in the whole society. So sources of change, technical issues or reviews by clients. When I built my home, my wife changed her mind to make a kitchen equipment something, and also toilet. They change the brand in the middle of work, right? So it takes time to. So this comes from client also to reviews. Clients return. And third party is something like vendors who make equipment. So it can be avoidable or unavoidable resistance. So that.
A basic question, but like for here, right? Um, when I did it outright, this becomes shorted, right? That becomes shorted. But when I like redraw the circuit into this, right, and I see that this is equal to 6.
And then for suppliers, because supply chain is more and more important rather than. So in old days, usually companies, manufacturers do making their PCs inside the factory. So 100 years ago, the Ford company, Ford Motors, there is about 10,000, no, 100,000 people working in a one single factory. So most of, including the steel plate and tire, they made on site 100 years ago. Nowadays, most of the parts is out purchased, right? Supply chain is more and more important. So the problem is you need to control the people outside of the factory. Scheduling mostly, right? Control your suppliers or subcontractors, the vendors. Comparing to the 100 years ago, there are a lot more coming from outsourcing. So that you need to have a more contract. Inspection, supplier work, and test type, and quality, delivery, and quality is also very. If one of the piece of million parts have a problem of quality, then the whole system can be have a problem. So quality control is also complicated. 100 years ago, it was also important for quality control. But the quality control is between companies. Right? And more is coming from outside. So then management of quality control is also. And also scheduling together. Project organization and project management, PM, engineering manager, this is design office, procurement manager, and construction site manager, okay? And also only scheduling manager. Scheduling manager has a cost of control. Process design also comes from chemical engineering. Right? So process building, they always have many short names, process flow diagram, material balance, say something like we have a air conditioning, you need to have a heat balance between cooling and there is a heat pump outside, right? So heat balance calculation, right? Something like this one is material balance. And then which equipment should be purchased to make this air conditioning? You have a compressor, piping, fans, and electricity, motors, right? As the equipment data. And then, so PNID is a diagram, right? And then operation, how can we operate this chemical process? More detail. Offshore structure, water plant, and process only for chemical process. More details on chemical process. Design basis or design criteria or requirements coming from the oil major, Shell, and design factor, PNID is output. Before then, there is also other calculation or data sheet. Process equipment, process instruments, utility equipment, utility instrument. Okay. So before then, there is a process flow diagram or utility flow diagram. Many short names. This is a sample of PNID. Piping and instrumentation and diagram. But this is a simpler diagram. Simpler means there is no size. Right? This is only just showing the items and connections. Connectivity. So between, say, membrane module or pump and valve, this is valve. And buffer solution tank, something like the tank. And then after that, you need to make a real drawing for the construction or installation. This is for the just conceptual. Then coming from this PNID, you can make a list of purchases, list of equipment, and also pipes. Right? But pipe needs to have a more detailed diagram or drawings to calculate the length is X. This is only for equipment and tank and something. Oh, yeah.
In many of our RealPARS videos, we discuss control system and instrumentation devices in great detail, so you can understand exactly how they work. In this video, we will learn how to read a P&ID, which is something that engineers encounter on a daily basis. At RealPARS, we love helping you learn. So if you enjoyed this video as much as we enjoyed making it, click the like button. Subscribe and click the bell, and you'll receive notifications of new RealPARS videos, so you'll never miss another one. P&IDs, or piping and instrumentation diagrams to give them their full name, are schematic representations of pipelines, equipment, instrumentation, and control systems found in process environments such as oil refineries, chemical plants, paper mills, and cement plants, etc. The symbols contained in P&IDs represent the equipment in the process, such as actuators, sensors, and controllers. Process equipment such as valves, instruments, and pipelines are identified by codes and symbols. As well as devices and pipelines, a P&ID will commonly contain information on vents, drains, and sampling lines, as well as flow directions, control I/O, and interconnection references. The instrumentation codes listed in P&IDs follow a standard format. After some practice in reading P&IDs, you'll know these codes by heart. But in the meantime, there are many resources on the web where you can download these tables for reference. The first letter of the code identifies the parameters that are being controlled or monitored. For example, flow, temperature, level, or pressure. The next letter is used to define the type of control device being used. For example, transmitter, valve, or controller. The number refers to the logical numerator. For example, we may have a system with 4 temperature transmitters. It makes sense to identify these as TTO1, TTO2, TTO3, and TTO4. Let's consider for a moment an instrument on a P&ID named FV01. Looking up the code for this, we could tell this is a flow valve numbered 01. Symbols, circles, and lines are used to represent instruments and to show how they are connected to the rest of the system.
For today. Process design. Again, the chemical process design, they produce PFD. Full name is not shown here, P&ID. Then the P&ID, based on this one, we need to have a piping instrumentation and PFD and H&M, balance, heat and material balance, process data sheets, something like Excel file. Then you can get equipment specification and purchase. And then purchasing means you need contact with the vendors. and then to provide the drawings so that we can continue. And this is another last slide on topside engineering. Topside means top part of the ocean plant. Ocean plant is made of, say, the floating body, substructure, and topside is some kind of plant of similar to land-based plant. Say that, as I told you that floating nuclear power plant is the nuclear power plant is as a topside of floating body. Right? Aircraft carrier, floating body, airbase, cruise ship, floating body, hotel, right? Something like this one. So topside for this case is a chemical plant. Usually the oil and gas treatment plant, refinery something. The design basic is chemical process simulation, PFD, UFD, and PNID. So you'll see that most of them coming to PNID. And then electricity is coming somehow, including PNID too. Okay. Question? Question? And enjoy the discussion session. For this discussion. It is document tense. First, let's have a quiz. There's the sequence of the life cycle. This is for the first one. And then and second one. Yeah. The third one is detailed decision. This is the answer. Concept screening is the initial stage of brainstorming. So it's for the project's feasibility and the primary goals and requirements.
for FEED, which is front-end engineering design. The detailed requirements before, it's for detailed requirements before full-scale design, and it is for developing initial design. And lastly, the detailed design is completing precise drawings and technical patient. Next, let's see about what the front end engineering design is.
Hello friends, welcome to our channel Piping Mantra. In this video we are going to discuss briefly about feed in perspective of piping. So let's discuss about what is feed. Feed stands for front end engineering design. The feed is basic engineering which comes after the conceptual design or feasibility study. The front end engineering design is the process that take an idea and turn it into a design. It consists of an input, which is an idea, and change into the current product, which we call output or a final design or a process. The feed can be divided into separate packages covering different portions of the project. The feed package is used as a basis for bidding the execution phase contracts like EPC, EPCI, etc. Feed takes into account everything related to the project before actual steps are taken. The feed focuses on the technical requirement as well as rough investment cost of the project and are used for the design basis. Based on the extent of detailing and stage, feed can be defined as basic feed, intermediate feed or extended feed. We will explain the difference later. Feed shall reflect all the client project specific requirement so that significant changes during the execution phase are avoided. During the feed phase, there shall be close communication between client, which should also involve the maintenance and operation team from the client side, and the feed contractor to work up the project specific requirement. The feasibility study evaluates the project's potential for success, analysis for the potential for the proposed project, which is based on extensive investigation and research to support the process for decision making. Feasibility study is the starting point of the feed. Let's see what are the deliverable requirements for the feed. As I said, this video is only for the perspective of the piping. We can see, like if we go for the basic feed, we need overall plot plan, piping material specification. So normally we have to give only brief description, tie-in details, and deliverable requirement for the intermediate or extended feed like overall plot plan, piping material specification, piping purchase specification, piping layout design basis, piping stress analysis design basis, concept note on overall plot plan, tie-in detail, interface register, demolition scope and detailed drawings, list of important assumptions, basis upon which the design is based, extent of engineering carried out at feed stage, outlining major engineering challenges or issues that need to be resolved during detailed engineering for extended feed. One or many of the following
For feed in ocean flex, what can be considered? First, about the design optimization for extreme environments. Ocean plants operates in harsh conditions, so these extreme factors take into account to optimize structure stability. And for cost, offshore projects are expensive and challenging. So by considering it, here's estimation of equipment and materials help to reduce overall cost. And for establishing operational and maintenance plans, so that the project enhance operational efficiency over its lifespan. Also, for environmental and regulatory compliance, environment is highly sensitive, so must be minimized their impact. It includes environmental impact assessment and development of environmental protection plans. Also, for safety assurance is top priority in design for both human and environment. So through thoroughly safety analysis, incorporating emergency preparedness into design. And lastly, I think the complex procurement and logistic planning is also important. Ocean plants are located far from shore, making equipment and material procurement during the essential items are identified. And this is all for my discussion. Question.
It's time for discussion session. And also lectures. Then press A, see you want to. Right. All right.